Okay, so welcome everybody to this Spark meetup. It's a really special one because we're actually live streaming to the internet now, so I'm really excited about this. I have this special tracker device and it's the first time, so probably will break halfway, I guess. So we're really excited to have the speakers today. So this is the program. I think most of you read it on the internet. So first we'll have a deep learning and Spark presentation by Matei. Really happy to have him here. And then the second speakers are Jelte and Rutger, talking about pattern recognition on Spark. So two really exciting topics, I think. A little bit about me. Probably most of you already seen this one slide before. So I have a PhD in parallel computing. I'm a data hacker at GoDataDriven, company which is housed here. And a data hacker basically, in my case, means I'm a data scientist and/or engineer, depending on the client, mostly. But nowadays, I basically drink coffee a lot while waiting for this. This is GitLab CI deploying a new Airflow stream. So a little bit about our sponsor. Last slide, then we'll continue with the actual stuff. So GoDataDriven started with Hadoop in 2009 with our initial customer bol.com. It's part of the Xibia group, which is a larger consultant in the Netherlands. Like 300 people in the Netherlands and a bit more worldwide. And we actually have like 25 data scientists, data engineers. A lot of us have a PhD, but it's not a requirement. And we're always looking for new people to join. It's like the saying. So without further ado, I'll give the floor to Matei, our first speaker.
All right, thanks. Okay, hello. Can you hear me? Yeah. Okay. So let me just get this thing plugged in here. Okay. Today I happen to be passing through Amsterdam to work at the Databricks office here because we have an engineering office here, you know, I thought to give a talk at the meetup. So I'm going to talk mostly about some of the new things that are being developed for Apache Spark, especially things that we're working on at Databricks with deep learning and streaming. And these are both kind of projects and work that's been underway for a while, and you can find longer presentations about them too, but I just want to give a brief overview and then hopefully have a bunch of time to answer questions as well. And deep learning and streaming are two of the sort of newest types of applications of big data where you know, where people are really trying to build new things. So they're also two of the sort of hardest things to do today with current technology. So I want to talk about how we're trying to make that easier using Spark and also using new libraries and systems that we're putting out next to Spark. So to talk a little bit about that and to explain where we're coming from, I also want to briefly explain how we thought about this for just simple kind of big data processing to begin with. And the reason for that is because I think that streaming and deep learning are in a similar place today. So early on, when companies like Google and Yahoo began doing these very large-scale computations on commodity clusters, it was very clear to everyone that these things have tremendous potential. You could ask a lot of questions that you just couldn't before. You could store lots of data, and you could build very powerful applications using it, like say Google Search or you know, anything of that form. But all these systems are also quite hard to use at first. Makes sense because they're kind of cutting-edge new applications. And in particular, when you know, when I started working on Spark at Berkeley, I had worked with lots of users of Hadoop before I actually worked on Hadoop itself before working on Spark, and I saw kind of two problems. So the first problem was that there were just very low-level APIs. They were designed for kind of hardcore, you know, software engineering experts, and you just had to write lots of low-level code. And then the second problem was that there were many different systems you had to hook together to build a big data application. So in particular, in companies like Google early on, and also in the open source world, whenever there came a new workload that people wanted to run at scale on a on a 1,000-node cluster, they would design a new distributed system and programming model for it. So if you have simple like extract, transform, and load, you had MapReduce at Google. If you had graph processing, you had Parallel, which was this API for doing graphs. If you had machine learning, there were separate systems for that. If you had streaming, there were systems like Storm or Millwheel at Google, and so on. While it is fun to build these distributed systems and APIs, it's very painful then to put them together and really get a reliable application. So in Spark, the main thing that we did, we basically did two things to try to tackle this problem and to really make it much easier to write these applications. The first thing is we focused on composable high-level APIs. So you don't have to write lots of code. And furthermore, if someone else writes some code, you can package it up into a function and call it. And it's still going to be efficient. For example, it gets pipelined with your other execution and stuff like that. So that's the first thing in Spark that's been expanding ever since. And what it means is way more users can write these applications, especially using the high-level APIs like Dataframes, for example, where they don't need to look under the covers and figure out all the maps and reducers that are going on. And then the second thing we did is to actually execute this stuff. The API is definitely nice, but it also needs to have acceptable performance and to actually be able to run your application. So we had this unified engine, which we designed to support batch, interactive, and streaming, and to basically support the things that people are building these specialized engines for. And it turns out, you didn't need to do too much for that. You just needed to take basically map and reduce and add some kind of data sharing, which is RDDs, and then you could already do these things really efficiently. So this makes it easy to build end-to-end apps. So today I'm going to talk about expanding Spark in two new areas, and at least the way we view it, we think these areas are also kind of early on and kind of in the same space as these MapReduce and other systems early on. So we want to make it much easier to build end-to-end applications in these areas using high-level APIs. And I'll talk about streaming, structured streaming in particular, which is part of Spark, and about deep learning, where Databricks has released a new package to do that. That's still very early on, but that I want to talk about. So let's start with streaming. So real-time applications are really becoming kind of important today, and they're kind of a necessary step to put big data in production. So basically, once people have done some interesting analysis, say you do the analysis and now you can run it every week or every day, people ask, hey, why don't we run this continuously and maybe even try to make some decisions in real time? Or once you've trained your great sort of machine learning model, you want to apply it to new data. But usually building these applications is quite difficult. So usually they do involve many different systems. They involve some kind of stream processing system, but also serving systems, storage systems, like where you're going to actually store your model or your input data, and things like that. And they also involve different APIs. So for example, if your streaming or real-time application takes in some data that's produced by a batch job, you need to make sure that whatever system you're using for batch produces consistent answers and has the exact same functions and computes every metric in the same way. And that can easily be a source of problems if you coded up something differently in one versus the other. And the other thing that makes it hard is that the interactions between these things and the external world is complex. So if you get a system like, say you get something like Spark Streaming or Apache Flink, it's very good. Like if you're just doing a map function or a group by or something like that, it knows how to do that, and it knows how to compute each thing exactly once and keep track of that. But as soon as you try to plug that into some external system, like you try to make it output stuff transactionally to a key value store or join against a file in HDFS in a transactional manner or something like that, that often tends to become user code where you need to understand the semantics of it and make it do that stuff. So, every time you're writing for each or you're writing kind of custom code that does transactions on an external system, you're starting to do the job that these distributed system developers are doing. And that's when we talk with users, that's often the most complex part for them with streaming. It's not, they never just want to run map on a stream, which there are great APIs for, but they want to say, take data in S3 and put the results in MySQL and count everything only once and make that work even though there's eventual consistency in S3. That's the kind of thing that they want. And then the final thing is that it is also hard to operate and debug these things. Again, once you have that application running, what if you find a bug and you want to upgrade the code? How do you even know, where it left off and how to continue? So our goal with structured streaming is to create an end-to-end API that covers not just the computation on the stream, but also the input and output and the interactions with other systems. So for example, if you're trying to do ad hoc queries on the stream, well, you can just use Spark and run a SQL query, and it will run on some consistent snapshot of it, and you'll get results that make sense. Or if you want to plug into S3 or into Kafka or into different data sources, all the ones that are built in will automatically be designed to have transactional semantics with the rest of the engine. So that's what we're trying to do. So structured streaming is this higher level streaming API that we've been developing. It's started last year, and now just a few weeks ago with Apache Spark 2.2, it's marked as GA. So it's kind of the API is stable and it's generally available. It has all the kind of basic features that you'll need. And it gives you kind of three things. So it gives you a simple API. It's really, I think, kind of the simplest possible API for a streaming system. And it's one of the things that sets it apart from kind of the dedicated streaming-only systems, because the API is just give us a data frame computation or a SQL computation, and we'll give you the same result as that, but just update it incrementally. So as long as you know what the data frame API does and you know how to compute your result, you can put that in and you'll get the same result as if you just stop the world at some point in time and ran that job on your data. And the API also naturally supports things like event time and out of order data. When data comes late, you can specify exactly how it should deal with that, the same way you would if you had late data or like out of order data in a file in HDFS. The second part is the end-to-end exactly once. As I talked about, we're designing both the sources and sinks and the ad hoc queries to actually have a consistent semantics. And finally, we want structured streaming to support the complete application lifecycle. So for example, one of my favorite features in it is you can upgrade the code as long as you keep the overall structure of the query the same. You can upgrade things like user-defined functions and so on, and have it pick off exactly where it left off. Or you can even dial back to a specific point in the input stream and correct your data starting then by working with the offsets that it produces. So it's just kind of a nice feature. You don't realize you necessarily need it until you're running, and like one day you have to go back and fix stuff starting like a week ago, and it's hard to do that. So this is GA in Spark 2.2, and I just want to talk about a couple of things with it, in case you haven't seen it in too much detail. So first thing, I want to talk about the APIs, and as an example of an application, I'll use this really kind of simple but sort of relevant event time aggregation thing, which is the Yahoo benchmark. So this is a benchmark, and I'll show the code first in Kafka Streams actually, which is a more traditional streaming only Java-based system. So this is a kind of representative application for analyzing a click stream. So basically, you've got some clicks that come in, and you try to filter out the click type to pick a specific type. And then for each click, you want to look up, it has this field called campaign ID, and you want to look that up with inside a campaign stable. So you want to figure out some information about the campaign that it's part of, and that's a join against this table, which is the campaigns. And so you have to do that. And now, so this is you're looking stuff up in some external system. And then finally, now that you know which campaign it's part of, you want to do a group and windowed count, and you want to window it by time. So this is actually windowing by the time field in the event, and these could come out of order, so you need to keep state, going a while back and be able to update counts in the past and stuff like that. So it's not bad to write it in something like Kafka Streams, especially with Java 8 with the closures and stuff, but there's still a lot of boilerplate stuff. There's all this stuff about types everywhere and making sure that the types match. There's like deserialization is part of your code. So if you wanted to take this code and run it on a stream that instead of being JSON it's something else, you'd have to go in the middle of it and change that stuff. And it's like relatively low level operations. So if you want to do this with Spark data frames, you can just write this thing as a data frame-based query and just use the API you're familiar with there. All the operations you're doing in this are simple things like maps and group bys and joins and things like that that already exist in the data frame API. So you can just write that, and events could be just a file in this thing, and then it would run as a batch job. But if you make events be a stream, like a Kafka stream, then it will simply run it as a streaming job. So pretty simple, and you get to use all the stuff you already know. And then, in fact, if you want to be even higher level, you can just use SQL as well. SQL and data frames get compiled down to the same thing. So one really cool thing here is you can expose streaming data to users in your organization who don't even know how to use Spark, or you can let them do, like maybe they can write a SQL expression or something like that you put into the query. And again, it will run the same way. So under the covers, how does it work? Well, structured streaming takes your data frame or data set or SQL code and compiles it to an operator plan, the same way that it would for normal Spark running on batch. So this is just basically like a database query plan. And then it compiles this to an optimized physical plan. It actually applies all the same optimizations you'd get on batch data, so things like code generation and pushing filters down and reordering expressions and stuff like that. But the final thing it does is it takes the plan and takes this one-time plan and turns it into an incremental one. So it decides, okay, what do I need to do to keep updating the result as new data comes in? And in particular, it's not really shown in the picture, but it can also maintain state between each time it runs and update that state as new data arrives as well. So that just happens automatically as long as the query has operators that it knows how to incrementalize. So basically, you just need to write the query the way you normally would, and this figures out how to run it incrementally. So that's kind of the high-level API. It's definitely really nice if you already know how to use Spark, and also if you want to expose this to to other users who maybe just know SQL. But often when you have a high-level API, you might lose out, for example, on performance. So maybe with that Kafka Streams one, if I can write those map functions precisely and stuff, maybe I can make it faster. It turns out, though, that actually structured streaming also performs really well. And in fact, we were pretty surprised that it's possible to go quite a bit faster than a lot of the existing streaming systems out there that people are using at scale. So just as an example, this Yahoo benchmark is actually one that a lot of people have optimized for, or have tested their systems for, because Yahoo initially published about it, comparing Storm and other systems. And I'm just going to show 3 different systems here, and they're all set to achieve roughly the same latency, which is around 200 milliseconds. Oops, sorry, let me skip this, because there's always a trade-off between throughput and latency in every system. Like the more you push stuff through, the more there'll be queues and things that increase latency. But all these systems can trade off between the two. So we ran the benchmark with Kafka Streams, and it was able, this is on 10 nodes, I think, and it was able to process around 700,000 records per second and do the join and do the group by, which is not bad. I mean, it's a lot of records per second, but it's running on 10 nodes. We ran Apache Flink, and it was able to do around 15 million. And then we ran structured streaming, just kind of the data frame code that I showed before, and it was able to do around 65 million. And this is, again, on the same cluster. Actually, the number is the number that was published by Data Artisans for Flink on a similar configuration. So what's going on? Why is it going fast? Well, structured streaming actually uses everything that's in the Spark SQL engine, which the community has spent a ton of time optimizing for very fast SQL, on large amounts of data. So in particular, it uses the Spark SQL optimizer, everything that can move expressions around and simplify them and so on. Now that doesn't really kick in here because this is such a simple query, but it can kick in other cases, and it uses the Tungsten execution engine, including whole stage code generation, off-heap storage, and so on. And it's a really nice way to just reuse this effort. If we spend 2 or 3 years building this kind of fast SQL engine with connectors to all these Java data sources, why not use it for streaming too? So what it means concretely for streaming is that these are actually pretty expensive applications to run normally because they're running 24/7. So it's going about 5 times faster. It means you can have 5 times lower cost in running your application, and that really starts to matter. The other thing that's kind of nice about this is if you run on fewer nodes, there are just fewer chances for things to go wrong. If you don't have to deal with failures, with rollbacks coming up. If you have 5 times fewer nodes, those things happen 5 times less often. So we're really excited to see this, and we think we can actually optimize even more for this, but it's just a nice benefit of running on top of Spark. So that's throughput, but the other question people ask is, what about latency? What if I really want something with super low latency, and I don't need a lot of volume per second, but I just want latency to be super low? For example, a common use case we see for this is you read from one stream, like say one Kafka or Kinesis topic, and you just put stuff into another one for other jobs to consume. So this is an area that Spark streaming wasn't very capable of doing well, because the Spark streaming API was based on this concept of micro batches, which like in the API we told you, hey, we're only going to run every 100 milliseconds or something like that. So we couldn't just make that faster underneath there. But in structured streaming, it turns out that we actually designed the API to let it update the results as often as possible. So the API is no longer tied to micro-batch execution. You can, because the API is just give us a query and we'll run it and we'll give you these updated results. And in particular, at Databricks, we've been developing this continuous processing mode that can execute structured streaming queries without micro-batch. Just simple, read events from one socket, write them to a different socket. And this is able to get sub-millisecond latency, the same as all these other systems at the same throughput that they're getting this latency at. And there's no changes to the user code. It's the same code you had before. So this is still early on. We actually had a demo of this about a month ago at Spark Summit in San Francisco. And there's an open issue to track it. And there's also a blog post with more detail. But this is something that the streaming team at Databricks is working on and wants to, to actually release kind of a first prototype of in the next few months. Okay. And that's kind of a bit about the performance side. And then the final thing I want to talk about is a little bit about use cases. So what are people doing with this? And this is an area where we've also seen really rapid growth of use cases and some really interesting ones, partly because the API is very easy to get started with if you're already using Spark. So I'll just talk about 3 use cases briefly. The first one I want to talk about is Databricks itself. So Databricks, if you're not familiar with it, it's a company that was started by the team that developed Spark back at UC Berkeley. It's based in San Francisco, and it provides a cloud platform to do big data analysis using obviously Apache Spark and also other technologies. It has actually over 500 companies now that are using this platform. So just running this thing, keeping those 500 organizations, each with many Spark clusters, running continuously is actually pretty challenging. And we decided to use Spark, of course, to monitor our own cloud service. And it's the best way to actually learn what are the challenges with something in production is to have to do it yourself. So right now, the metrics pipeline that we have is processing about 14 billion events per hour using structured streaming, and it's running on 10 nodes. We actually started this, as soon as we developed even the first kind of basic version of structured streaming. Before it was GA, we were already using it ourselves because we really wanted to understand, what's hard about using it and how can we make it better. So this pipeline powers a bunch of different applications. So it powers ETL, which is, we receive these logs from our services and from all the Spark executors running on customer workloads and stuff like that. And we just need to clean them up, normalize them, and store them historically. We store them into Parquet for historical data. It's used for dashboards where people watch it. Actually, every team at Databricks has a dashboard on the monitor, next to where they sit in the office, where they see metrics for their specific application. Like, for example, how many streaming events have been processed this hour or stuff like that. It's used for alerts to notify engineers when problems are happening. And it's also used for ad hoc analysis, where you want to go in as something is happening and actually query the latest data. And the way it works internally, it's actually a combination of basically Kafka and Parquet on Amazon S3. So we get this stream that comes in, if I can find this. So yeah, we get these metrics that go into a Kafka stream, and we have some jobs that go that directly filter the data in Kafka and send out alerts. These are the ones that are often very latency sensitive. And then we have other jobs where we ETL things into Parquet, and then we display dashboards or we do ad hoc queries. And there are actually many, like several dozen queries and dashboards and plots hanging off this single pipeline. So anyone can add one, just query the stuff in Parquet and have a nice real-time dashboard. And this, it's actually it's been taken up basically by all the teams, and it's made it super easy for anyone to build one of these dashboards for their area of the product. The other two use cases I want to briefly mention are two that gave talks at the Spark Summit. They're both customers of Databricks as well, who used structured streaming early on. So Viacom and iPass. Viacom runs lots of online media properties, and for the online video and all those properties, they're using structured streaming to monitor its quality and to figure out things like, hey, this ISP's connection to our video server is bad, or this content delivery network is having problems, or things like that. So that's an important kind of real production monitoring application for them. And iPass is actually the world's largest provider of Wi-Fi hotspots. Like them or hate them, I guess, but it's a pretty good service. And they're using this to monitor the data from all these Wi-Fi hotspots. So each time those hotspots aren't working, you know how frustrating it is. So and iPass also knows. So they're trying to fix it. Both of them gave talks at Spark Summit, so you can actually check those out online to see what they spoke about. Okay. So that's kind of the streaming part. Hopefully it gives you an idea of how providing basically this end-to-end streaming system that's integrated into Spark enables these applications. So anyone can do ad hoc queries, can do reporting, can do ETL to many many different data things and so on. The second one I want to talk about briefly is deep learning. So deep learning is, of course, the kind of the exciting new method in machine learning, and it really has a kind of a lot of potential, because deep learning combined with the large data sets that are available now finally make it possible to featureize and start using a lot of data that before wasn't really usable in machine learning, in particular images and text. These kind of unstructured data. And basically the main point, the main way that deep learning does this is by automatically learning feature representation. So it has this, this network of simple units or simple, say, linear functions or something close to a linear function. But then by hooking lots of them together and training it in the right way, you can learn features of increasing complexity in the data. So you can learn to discover things like edges and circles and things like that. And eventually, once you get to enough features, you actually have built useful feature representations of this type of data. But deep learning, as it is today, is also quite difficult to use. I'm sure anyone who's tried it has dealt with some of the pain. So the current APIs are pretty low level. They're really designed for kind of machine learning experts who want to build all these operator graphs by hand. So you have to build this whole graph by hand of these operators. And also, if you want to scale out, it's often not a first-class concept in the APIs. You have to, in the best case, you have to manually write code that will distribute your model. You have to say, okay, this part will be on this machine, this many nodes will be parameter servers, and so on. So it's just a bunch of manual work you have to do. And then the second problem is after you've trained your model, using it in an application can also be difficult. So for example, with TensorFlow, you have TensorFlow serving, which is good if you want to do REST like API requests. But if you just want to call this thing, say, inside a Spark job or inside a mobile application or something like that, it's not as easy. You don't want to be calling a server all the time. So this is also an area where you have to do a bunch of engineering. So it's definitely not insurmountable, but it is a lot of work, and a bunch of the work is pretty mechanical. And this reminds me a bit of, again, these kind of early big data APIs where you just had to do lots of legwork to get something done. So our goal with this package at Databricks is that we want to enable an order of magnitude more users to build applications using deep learning, and we just want to make it super easy to do the common use cases at scale. So we're designing this API deep learning pipelines that focuses specifically on these end-to-end use cases, not on just giving you the knobs to build something from scratch, and also where everything you use automatically scales out of the box, so you don't have to do extra work for that. So deep learning pipelines is a high-level API for deep learning that integrates into Spark's machine learning pipelines, which are a nice way to set up machine learning as a sequence of transformations on the data and then model estimators and also ways to evaluate the models. So the goal is common use cases should just be a few lines of code, not copy and pasting a giant thing from the TensorFlow tutorial. And everything should also automatically scale out using Spark. And then finally, once you actually build a model, we want to make it very easy to use in the rest of Spark. So this is the second kind of area that this tries to enable. And internally, it builds on existing deep learning engines that that will run underneath. So TensorFlow is the one we currently use. We also want to expand it to work on Keras and BigDL and PyTorch and sort of other frameworks where it makes sense to use them. So I'll just give you a small kind of tour of the things you can do with it, and why we think it's nice to do this deep learning stuff inside Spark. I'll start with just loading some data. So if you want to load images, one of the first things in the deep learning pipelines package is a way to load images into data frames and represent them basically as structs inside Spark SQL. So you can read images from a directory and get back a data frame that contains these structs with different fields, like the mode of the image, the height, the data, and so on. This is kind of a visual representation. And internally, they're stored in the same way as all the other data in Spark SQL would be. The second thing that it makes it easy to do is to work with models. And the easiest way to do that is to work with an existing deep learning model that someone else trained. There are really good ones available from people who've spent lots of time training these at Microsoft and Google and so on. So we take these models and turn them into ML Lib transformers. So a transformer, if you're not familiar with MLlib, it's basically just a function that takes an input data frame and produces an output data frame, and it can transform one or more columns in it using different parameters. So if you've got this image data set from before, you can add a column to it, for example, called predicted labels, and you can use this Inception V3, which is a trained sort of state-of-the-art model from Google that you can just apply. And it recognizes, this one recognizes about 9,000 classes of objects as part of the ImageNet benchmark. So just applying that on a bunch of images, you get these like predicted labels, and again, it's easy to represent them in a data frame in Spark, and then you can use your favorite SQL or data frame API to select stuff in them. So that's that's one thing. Now this is kind of nice, but in reality, using these pre-trained models isn't that great unless the things you're looking for are exactly the classes in the ImageNet benchmark, like strawberries and bees and daisies and stuff like that. And also your data is like pretty similar to it. So this isn't always the only thing you want to do. There are, for example, a lot of use cases I've seen where you just want to recognize, say, people, and the ImageNet people classifier is good enough, and you just run this and call it a day. So the next level of model training that people do is usually transfer learning. So transfer learning is a quick way to train a model for your specific data set and also leverage information from these large pre-trained models that have been trained on, say, millions of images or text, characters, or things like that. So I'll just give a small example of how you may want to do this. Let's say you just want to do binary classification, and you have, say, images of James Bond cars and then other cars, and you just want to find these. That's an example application where transfer learning will be pretty good. The data is images, and you can get some labeled data. It's you can find some of these in the Bond movies. You can just take pictures of other cars on the street. I think I've seen this one in Amsterdam. So, I saw something pretty similar to it, so you can just get that. But actually, it's actually pretty hard in this application to obtain lots of training data. Like, for example, getting millions of images of James Bond, because James Bond is pretty elusive. So it's actually very hard to train a machine learning model from scratch, a deep learning model from scratch, because you don't have enough data. It will just overfit if you try to do that. So this is where transfer learning is very powerful. So transfer learning uses the features that were learned by one of these large models and then just applies them to your specific data to train a classifier on top. So if we take this ImageNet model I showed before, the inception one, internally, each of its layers is kind of learning these next generation features of more and more complex features of the image and basically figuring out which pixels they apply for. So as you go through, it learns these more and more abstract representations and higher level things like eyes and panda faces and stuff like that. And at the end, usually these models just add a classifier, softmax, which is the same thing as logistic regression, and basically they can predict probability of this thing being in different classes. It turns out, though, that if you have learned these intermediate features, they're also useful for new classes that don't appear in the original data, because you've just learned common properties of images, just common things you see in an image, like this angle or the shiny reflection of a car or something like that. And so you can actually take this and just cut off the last layer, the softmax, and take the features and just train a simple classifier, like just a logistic regression or something like that, and apply it to your 007 data. And you'll actually get a pretty good image classifier for your specific data. So this is, for example, the technique that's been used in a lot of the medical work with deep learning. When you read about people automatically diagnosing cancer from images or something like that, they don't have millions of cancer images the same way you have millions of images of pandas on the web, but they can take this type of model and do this transfer learning to apply it to that. So this is really easy to express in an ML pipeline in Spark. Basically, you do your image loading and preprocessing, and you apply this deep image featureizer, which is the first part of the network, and then you just train the second part. Here I'm training one layer of logistic regression. If you want, you can also train multiple layers using the neural network module in MLlib. So it's easy to draw, and it's also easy to implement. So using this package, you can just take the deep image featureizer with the pre-trained model Inception v3, add a logistic regression, and put it in a pipeline. And this will automatically work on any data you feed in from Spark, and it will automatically be distributed on the cluster too. So just as an example, here are some pictures that it gives, and the probability or whatever the likelihood that it's a James Bond picture, and it's definitely learning features of James Bond. Okay, so that's kind of a second use case that we made super easy. the third use case that, that we want to support is distributed model tuning. This is actually not completely out yet, but it's almost done, and it should be out in the open source package soon. So why do you need to do model tuning? Well, I think anyone who does machine learning has perhaps seen this. So this is how machine learning actually works under the box. So maybe, I don't know if you've seen it, but basically you ask, is this your machine learning system? Yep, it's just this pile of linear algebra stuff. And what do you do if it doesn't work? Well, you just keep mixing it up, keep changing some parameters until the answers are right. And this is basically what a lot of machine learning practitioners are doing every day. Though, of course, the way you mix it and stuff requires brilliance and a PhD and stuff like that. But yeah, there is research that also shows that just random search does pretty well at this, from what I've understood. So how do you do this? So if you're just going to try lots of parameters and they're each kind of pretty much independent, this is a great use case for distributed computing. And this is something that you can easily do with Spark. So you can just launch a Spark job and basically kick off a bunch of tasks. And in each task, you try a different version of your model. So for example, even in the transfer learning use case I talked about, you may want to try different featureizers. There's Inception, there's VGG, there are all these different ones that people have published. Why not try all of them and see which one's better? And you may want to try different classifiers after. Should we have logistic regression? Should we have maybe a two-layer neural network? Should we have random forest and so on? So that's an example of something you could do. And distributed model tuning also fits nicely into the ML Lib API, and the goal here is to just let you do it on an existing Spark cluster. So ML Lib already has a concept of parameter search for its pipeline. You can put in combinations of parameters you want to try, and if you use this in the API, the scarce image estimator, for example, you can pass in different parameters to it, and it will just try all of them and give you the best model. There are also other ways you can you can tune parameters of the other parts of the pipeline as well. So it's pretty easy to implement and to run. Okay. And then the final thing I want to talk about is sharing and applying models. So now you've built your machine learning model. It's really nice, but you want to let other people in your organization use it. And that can also be painful. That can require writing a bunch of code by hand and making it available. And that's something that we want to make easy, at least when the other people are using any of the APIs in Spark. So in particular, the thing we added here is the ability to take a ML pipeline or a deep learning model and expose it as a user-defined function in Spark SQL. And so as long as you're using SQL or Dataframes or structured streaming for that matter, you just call this function and apply it to a data point. So as an example, if you've got this Keras model that you trained, you can register it as a user-defined function, give it a name, and then in SQL, you can use it inside your SQL query and just apply it. Or you could use this in structured streaming or in Dataframes or anything like that. And the really nice thing about this is, the users don't even need to know about deep learning. They don't need to know how are you supposed to call a Keras model from Java and then call that from Spark. They can just put it in there. And maybe someone completely different from them is publishing these functions and they just use them in their day-to-day job. So really simple, but really nice to work with. And obviously, it works in all the different Spark APIs. So that's a brief overview of deep learning pipelines. There's a lot more that we're working on now, and there's also a lot of contribution happening from other companies in the community here. So in particular, one of the things being worked on now is distributed training of one model. So instead of parameter tuning, what if you want to just distribute the training of one model? And there's this really nice package from Yahoo called Tensorflow on Spark that does that. The team there is actually helping to integrate this with deep learning pipelines. So you can call it an ML pipelines. And then the second big area is just more built-in data types and more built-in models. So we started with images because they're really common, but we want to do the same thing for text and time series and so on. Yeah. And basically, to conclude, this is a high-level API for deep learning. Everything in it is designed to scale out by default. So all the things I showed will scale out. For TensorFlow and Spark, you need to do a bit of work in your TensorFlow code, but it's about as easy as it could, I guess, be to launch it on Spark. Also, all of the models you produce for it are designed to be usable everywhere else in Spark. That's kind of the goal. And if you want to check it out, it is on our GitHub. OK. So these are the things I wanted to talk about. Basically, to conclude, the way we think about things is there are these new use cases coming up for big data all the time, and every use case early on, people don't really know necessarily the best way to do it, the best practice, and so on. So you get interfaces that are specialized for it and are complex and often require lots of work to integrate with other things. But over time, once you find techniques like, say, transfer learning, which nearly everyone is using now to do image classification, it makes a lot of sense to try to fit these into these kind of unified frameworks, and that's what we're trying to do in Spark. So we're trying to package these things behind these composable high-level APIs to create lots of room for flexibility in the execution. So for example, have a streaming engine that's not just Java code we have to run exactly as is, but that we can transform, do things like optimizations and this continuous processing mode on. And finally, to let you hook them up in end-to-end applications. One last thing I want to mention, we do have a conference coming up in October in Dublin, and we'd love to see lots of people from Amsterdam there. And I received an exclusive discount code for the Amsterdam Spark Meetup that you can use to sign up if you want to check it out. And if you want to learn about Spark without flying to Dublin, one other thing we're doing is putting some free preview chapters of Spark the Definitive Guide, which is a book that Bill Chambers and I are writing, online on the Databricks website as well. So this is free. You can also check that out. So hope to see some people at least at Spark Summit. Thanks. Any questions? Yeah. Yeah.
I have questions related to the deep learning part.
Sure.
Maybe you already explained it, I just want to hear it confirmed. In case you have a running pipeline, streaming pipeline, which actually uses already a pre-trained model, and you have a new model, new version,
yeah.
Can you replace the model without stopping the pipeline?
Yeah. Yeah, you should be able to do that. Yeah, I think it will. I think the way you do it now is you would just register a UDF again, like you would register UDF with.
You can do this without.
Yeah, yeah, exactly. Yeah. Mm-hmm. Yeah. Yeah.
Do you also have plans to start using Microsoft's LightDB and to make it easy to use that process?
Oh, this is the decision tree system. Yeah. Yeah, that makes sense. Yeah, so actually this is something we've been looking at. Both that and XGBoost, you want to make it, like, I would love to have an API like this where they're just estimators inside Spark, where you can plug them in with the rest of the pipeline. So I don't know, I think we're looking at XGBoost first, but that would be nice. Yeah, if you know any of the developers there, maybe they'd be interested in doing that. Yeah, or at least in helping out with it. Yeah. We've seen that come up a lot. These are some of the more widely used things. Yeah.
I think XGBoost is basically the same as LightDB.
Mm-hmm.
Yeah.
It's not as fast. Okay. Well, maybe we should. Do, okay. Yeah. Yeah. No. I guess. Yeah. I'll have to look into them. I've seen a lot of people asking for both, but yeah, it would make sense. More generally, actually, another thing that I would like to see is, like for this and the TensorFlow thing, it would be nice to just have a standard way to launch like some other distributed system on the Spark nodes. So that's something that I'm hoping that we do also. That makes it easier for them. Yeah. Mm-hmm. Yeah.
You showed some like very well-known image recognition models. Are there some other models for text or audio?
Yeah, good question. Yeah. So right now, I think you can take any Keras model from. So Keras, for example, has these built-in models in its standard library. You can take those and easily import them. The one thing now in deep learning pipelines, it doesn't have first-class support for text. For example, it just has. You have to convert the text into a vector yourself and pass it in. So that's kind of a limitation. But once you do that, you can take those models and apply them. It doesn't care whether it's an image one or something else. Yeah.
Maybe you can build in the word embeddings or
Yeah. Yeah, we'd like to do that. Yeah, there is actually a word to vec in MLlib already, but we'd like to make it easy to put in these ones. Yeah. Yeah.
Do you have any data you can share about the time it takes to train a model compared to the state of
Oh, yeah, good question. Well, so transfer learning actually is you can train a model in just well, it depends how much data, but like you can train one in just a few minutes if you have a cluster. So this thing I showed, the James Bond thing, was actually our demo at Spark Summit West. You can actually find a video online, and that one I don't remember how many images they trained on, but you can do it in a few minutes. That particular thing also is pretty efficient on a CPU. It doesn't like. Basically, it's not really bound by flops in a significant way. If you want to do distributed training, so using many GPUs, it's actually a lot of work usually to tune things. So it is possible to scale things out, but most of it comes from like whether it works well or not will mostly come from how you tuned your system, basically. Which is, it's kind of unfair. But basically, the good news is we're not adding any overhead. But the bad news is you need to figure out how to set up TensorFlow or whatever to do that. Yeah. But people have gotten speed-ups with these, but it's a lot of work. A lot of people just train on one machine. That's one of the reasons we wanted to do the hyperparameter thing as well, because a lot of them, we see just want many copies of the same thing. Yeah.
Can you tell us something about recovery and streaming?
Recovery and streaming. Yeah, so I don't have a super detailed slide on it, but basically, if I can go back to it. Yeah, so basically as it's running, it will, as it's running, it will actually keep this write-ahead log that tells it how far it's gotten in the stream, and it keeps it in a way that's also consistent with the output sync. So for different output syncs, we have different ways of doing the commit to them when we commit the next sort of unit of data to that stream. And so you can actually, not only will it recover if a node fails or something, you can actually just kill the whole application, like just shut off the driver and everything, and just launch it again, and it will pick up where it left off. And this is what I mentioned about the maintenance stuff. So when I said, hey, maybe you want to upgrade your code, the checkpoints that it writes are stored in this JSON file that's designed to be easy for it to read, even if you upgrade your version of Spark slightly or if you upgrade your code. And it can take the JSON from before, parse it, and see where it left off. So that's how you would do that. Yeah. In fact, one of the modes, I should mention this too, like one cool thing you can do with structured streaming that we've seen people do is some people want the exactly one sort of semantics from the input to the output, but they don't want to keep nodes running 24/7. It's just too expensive. So you can even run this in a batch fashion where you just run kind of one micro batch at a time, but like say you do it every hour or every 2 hours, and then you use your cluster for something else, and it will remember where it left off. And even that's actually very valuable, because otherwise you would have to write a job that like exactly remembers what it was doing. Yeah.
I think that's going to be the last question. So let's thank the speaker for his talk. It was really great.
Okay. Cool.
And we can have a small drink at the bar, and then like in 15 minutes we'll reconvene for the second presentation. Thank you.
Whoa.